Hi, I'm Segel from the AUTOML group at Leibniz University, Hanover. I would like to present to you our work on symbolic explanations for hyperparameter optimization. This is a joint work with Helena Graf, Tornede, Bernd Bischl, and Marius Lindauer. So hyperparameter optimization methods are great at finding us well-performing configurations efficiently. However, a drawback here is that they usually do not provide a lot of insight or explanation into the HBO process and also the returned configuration. And this lack of transparency can then lead to missing trust of the users. Therefore, we would like to move towards a more human-centered and interpretable HBO process. And we suggest doing so by leveraging symbolic explanations. Symbolic explanations employ symbolic regression to learn an interpretable, easy-to-understand formula that describes the relationship between hyperparameter configurations and the performance of the model. These symbolic explanations have various practical applications. For example, because they provide insight into the HBO process, they can support practitioners when using or interacting with HBO tools. Second, because they actually provide an explicit formula describing the HBO loss landscape, they might also be useful for researchers to better understand the HBO loss landscape. So how do symbolic explanations work? Well, first of all, we start with the standard Bayesian optimization HBO process, meaning that we collect configurations, we evaluate them, and this then is our metadata, so the configurations and the corresponding performances, with which we train a surrogate model, which then again selects the next configuration to be evaluated. After this HBO process has finished, we take the metadata that we just collected and train a symbolic regression on it. The aim of the symbolic regression here is to find a simple mathematical formula describing the relationship between the hyperparameter configuration and the model performance. To do so, first a population is randomly initialized, then genetic operations are performed on that population of formulas, and the best performing formulas are selected and are then moved to the next generation. This is done for quite many generations until finally we obtain a formula that describes the metadata or fits the metadata quite well. And this final formula then is our symbolic explanation. Of course, there are some challenges here because, first of all, fitting the symbolic regression directly on the metadata collected during the HBO process, as I just explained, does not work too well in practice, which is due to the sampling bias caused by the HBO sampling strategy. One alternative here could, of course, be to use randomly sampled configurations and evaluate them using the true cost function, so actually training the machine learning model with each of these configurations. However, this is quite expensive because we would have to evaluate a lot of additional configurations. Therefore, we propose to use the best of both worlds, meaning that we use randomly collected configurations, but we do not evaluate them with the true cost function, but we approximate or predict their performance using the surrogate model that we trained during the HBO process. And these configurations are then what we would fit the symbolic regression on. So now here you can see how well the symbolic regression can predict the performance of unseen hyperparameter configurations. So what is shown is the root mean squared error between the cost predicted by the symbolic regression and the true cost for different machine learning models. We show the RMSE here for the symbolic regression, of course, with the different fitting strategies that I just described, and also for the Gaussian process surrogate model as a baseline. And furthermore, we also show the RMSE for a simple linear regression for comparison. So if you have a look at the symbolic regression that was fitted with the last approach, so leveraging the Gaussian process surrogate model, shown here in green, and compare it to the RMSE of the actual Gaussian process surrogate model, shown in red, you can see that they are quite close most of the time, which is great because that means that this symbolic regression approach is suitable to faithfully predict the performance of machine learning models based on the hyperparameter configuration. Another challenge that we faced here was that the resulting formulas must, of course, not be too large, because otherwise they are not really easily interpretable anymore. And to face that challenge, what we propose is to employ a regularization penalty based on the size of the formula. And this penalty involves a parsimony hyperparameter, and that can then be used to control the complexity of the formula. So how one would do this in practice to achieve a desired complexity could be to use elbow heuristic. With this elbow heuristic, the idea is to evaluate multiple values of the parsimony hyperparameter, for example, starting at a rather large one, which corresponds to a large RMSE but small complexity, and then step by step move towards smaller values of the parsimony parameter. And one could stop here, for example, if the RMSE, the decrease in the RMSE, does not outweigh the increase in complexity anymore. And this is then the final parsimony hyperparameter that one would use for the problem at hand. So to summarize, symbolic explanations can help us to learn an analytical closed-form expression to model the dependency between the model performance and the hyperparameter configuration. We show that it is possible to leverage the surrogate model to mitigate the HBO sampling bias and obtain a faithful symbolic model. Furthermore, we can control the trade-off between the symbolic model's faithfulness and the interpretability by using a parsimony hyperparameter. So the final takeaway here is that we can gain insights into the HBO process at little additional cost in the order of minutes using symbolic explanations. Of course, there are some open challenges. For example, it would be very helpful for users if we can quantify the uncertainty of the expressions obtained by symbolic regression. Furthermore, it would be quite interesting to investigate the properties of the resulting formulas to better understand the HBO loss landscape in general. So, thank you very much for your attention. And if you have questions or comments regarding our approach, please talk to us. Thank you.